In the first scenario, where there are 4 service panels in one building, with each panel having its own service transformer in separate buildings, each service panel and its associated loads must be treated independently from other service panels. This independence stems from the galvanic isolation provided by each separate service transformer. Galvanic isolation ensures that there is no direct electrical connection between the different service panels. Because of the independent source, bonding between these different service panels is not permitted. Connecting the grounding systems of separate service panels can create parallel paths for current flow. These parallel paths can lead to several safety hazards, including increased ground fault current, which may not be adequately cleared by overcurrent protection devices. Furthermore, circulating currents in the grounding system can cause electromagnetic interference and create touch potential hazards. Each service panel must have its own dedicated grounding electrode system installed according to the National Electrical Code, or NEC. This grounding electrode system typically consists of a grounding electrode conductor connected to a grounding electrode, such as a ground rod, ground ring, or metal water pipe. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors. The grounding electrode system must be properly bonded to the service equipment enclosure and the neutral conductor at the service entrance, as specified in NEC Section 250.24. All equipment grounding conductors must be connected to the service panel's grounding bus, providing a low impedance path for fault current to return to the source. This ensures that overcurrent protection devices will operate quickly to clear any ground faults, minimizing the risk of electrical shock. Proper separation and independent treatment of these service panels is crucial for maintaining electrical safety and preventing potential hazards associated with interconnected grounding systems. The second case involves a service panel in one building and several distribution panels located in a different building. In this scenario, the service panel and the distribution panel should be considered as one system for bonding purposes. This is because the distribution panels are directly connected to the service panel and receive their power from the same source. The electrical connection between the buildings necessitates a unified approach to bonding and grounding to ensure equipotential grounding throughout the entire system. Equipotential grounding means that all exposed conductive elements in both buildings are at the same electrical potential, minimizing the risk of electrical shock. Bonding should be performed between all exposed conductive elements in both buildings, including metal conduits, metal enclosures, and any other conductive parts that are likely to become energized. This bonding creates a low impedance path for fault current to flow back to the source, ensuring that overcurrent protection devices operate quickly and effectively. The grounding electrode system for the service panel should be extended to the second building, providing a common ground reference for both buildings. This can be accomplished by installing a grounding electrode conductor from the service panel to a grounding electrode in the second building. The grounding electrode in the second building should be bonded to all metallic water pipes, gas pipes, and other available electrodes to create a comprehensive grounding system. The size of the grounding electrode conductor must be determined according to NEC Table 250.66. based on the size of the service entrance conductors. In addition to the grounding electrode conductor, an equipment grounding conductor must be run with the feeder conductors from the service panel to the distribution panels in the second building. This equipment grounding conductor provides a fault current path and ensures that any fault current will flow back to the source, tripping the overcurrent protection device. The size of the equipment grounding conductor must be determined according to NEC Table 250.122, based on the size of the overcurrent protection device protecting the feeder conductors. It is essential to maintain the integrity of the grounding system throughout the entire installation. All connections must be made with approved connectors and properly tightened to ensure a low resistance connection. Any splices in the grounding conductors must be made with approved splicing methods and must maintain the integrity of the conductor. Regular inspections and testing of the grounding system should be performed to verify its effectiveness and ensure that all connections are secure and free from corrosion. By treating the service panel and distribution panels as one system for bonding, electrical safety is enhanced and the risk of electrical shock is minimized. It's also crucial to consult local electrical codes and regulations, as they may have additional requirements or restrictions regarding the installation and bonding of electrical systems in separate buildings. Maintaining accurate documentation of the electrical system, including wiring diagrams and grounding details, is essential for future maintenance and troubleshooting. In summary, the key differences in handling these two cases lie in the source of power and the galvanic isolation. Independent sources necessitate independent treatment, while interconnected systems require unified bonding. Proper adherence to electrical codes and standards is paramount in both scenarios to ensure the safety and reliability of the electrical installation.